Okay, so now we're going to solve this next example. If you're following along in the notes, this is the second, the name of the subsection this is in is called second example, which is a great name because it's the second example. So the equation is 3 times the t derivative of u plus the x derivative of u is equal to 0. And we know that u is equal to x squared on the line t is equal to minus 2x. So u is equal to x squared on the line t is equal to minus 2x. We'll graph all of this stuff in just a minute. Okay, so parameterization for the line, I can call this x naught and then minus 2 x naught, and this is going to be for x naught in R. Now here really theta might be a better choice than x naught. In fact, that's what I'm going to do, just to give an example of when I'm using theta instead of a different variable. Theta minus 2 theta. Okay, and this is going to be as theta goes in R. The reason I say theta might be better than x naught is because if I say x naught, we kind of get the idea that this is lying on the x-axis. Okay, again, you could do x naught, that's how I have it in the notes, but maybe I'll just do one with theta so you can sort of understand a little bit more about where the theta comes from if that seemed confusing. Okay, x prime is going to be whatever is multiplying the x derivative of u, which is 1. T prime is whatever is multiplying the t derivative, so that's 3. Z prime is going to be whatever the right-hand side of the equation is, so that's 0. X of 0 is going to be equal to that value there, which is theta. T of 0 is going to be that value there, which is minus 2 theta. And Z of 0 is going to be u evaluated at this point here. In other words, x squared, that's going to be theta squared. So Z of 0 is equal to theta squared. Okay, so again, in terms of systems of differential equations, you can't ask for anything much easier to solve than this. X of s is going to be equal to s plus theta. T of s is going to be equal to 3s minus 2 theta. And z of s, well, z is constant because z prime is equal to 0. And so z of 0 is just going to be equal to theta squared. Now, if we did like we did before and sketch these characteristic curves, again, remember the x and t, the curves defined by x and t are called the characteristics. We're going to get something like this. So this is x, this is t. This is a good problem for which it really doesn't make sense to think about t as being a time variable. We're going to think about x as being another spatial variable. At any rate, if I'm going to sketch the gamma curve here, I'm going to sketch it in blue. It's just x, it's just t is equal to minus 2x, so it's going to be a slope of minus 2 going through the origin. So it's going to look something like this. Okay, and then for every theta, I'm going to have a different theta here. This is a theta, particular theta value. This point, let me see, is theta minus 2 theta, but it's some theta value. And I'm going to have from that a characteristic given by this equation here. It's going to pass through this point here, and it's going to have a slope of 3. So it's going to look something like this. Again, I'm going to have a different characteristic here. It's going to have a slope, going up like that. Sorry, let me color code this. Let me give this a different color. So this is a different theta, and we're going to have a curve going up here. Okay, and so all along this black characteristic, for example, we know that u is going to equal to theta squared, and along this purple, we're going to have also u is equal to theta squared, but for the purple theta squared. Okay, and as we can see, the lines are also extending this way as well. This would be like going into negative s for the parameterization. Okay, And again, these are lines that are parallel with each other, but I'm not that great at drawing, and I'm kind of drawing sideways, so I'm even less amazing. All right, so then at any point on this line, we know u is equal to theta squared, but again, we don't write solutions to PDEs by saying it's constant on these lines, though geometrically that can definitely be helpful. What we typically do is we want to take a generic point in the plane, let's call it xt, and we want to know what u is equal to at this point here. Well, if I try to draw a line that's roughly parallel to these, okay, notice two things. I think it should be pretty clear that every point is going to lie on one of these lines because there's a different line of slope 3 through each one of these points here. And so each point is going to lie on one line, and that characteristic is going to intersect the curve gamma in one spot. The fact that it only intersects the curve in one spot is important. We'll start to see some examples. We'll see at least one or two examples where that's not going to happen, and we'll talk through it then. But it is important that it only intersects the point in one spot, and you can just think about that in terms of solving these equations. We want to see where this characteristic intersects the curve gamma. That's what we're doing when we solve for x naught and theta, or sorry, s and theta, or s and x naught, depending on what we're calling the variables. If it intersects the if it intersects gamma, if you have a characteristic that intersects gamma at more than once, there's going to be some ambiguity. Okay, so given this point xt, if we can find this value x naught, we know that u of xt is just, if you can find the value of theta that corresponds to this, we know that u of xt is just going to be equal to theta squared. Okay, well, how can we do that? Well, I know xt lies on this curve. For that, s plus theta and 3s minus 2 theta. So I know that x is equal to s plus theta, and I know t is equal to 3s minus 2 theta. Now the thing that I want to solve, the thing that I really want to know here is I want to know what theta is. I don't care about s in particular for this problem, though as I mentioned in the last video, sometimes z will depend explicitly on s. I only want to know what theta is. So whatever method you want to use to figure out what theta is, that's going to be fine. For example, if we look at this equation says theta is equal to x minus s. And then if we come down here and solve, figure out what s is equal to here, we get that t plus 2 theta over 3 is equal to s. And so now if you plug in this value for s up here, you get theta is equal to x minus t plus 2 theta, t plus 2 theta over 3. Now theta is the thing that I want to solve for here. So if I add 2 theta, if I add 2/3 theta to both sides, on the right hand side I'm going to have 5/3 theta, 5 theta over 3 is equal to x minus t over 3, or I can write that as x minus 3x minus t over 3. If I multiply by both sides by 3, I get theta is equal to 3x minus t over 5. So theta is equal to 3x minus t over 5. So that solving was a little bit clunky, but this system of equations right here is a system of algebraic equations. We just want to solve it in principle for theta and s, this just for theta, and this is what we get theta is. So then over here, I'll write the solution u of xt. Well, for this generic point xt, that's going to be equal to theta squared. But what is theta? Theta is 3x minus t over 5, and then we square it. Okay, and just like for the previous examples, I suggest that you show that this actually does solve this differential equation.